Good morning. So, we have covered 4 modules so far: the basics of fire, various terminologies, non-dimensional numbers, etc. we have seen here. Then, review of thermochemistry, chemical equilibrium and kinetics was done in the second module. So, the air calculation for a particular fuel and the products of combustion, adiabatic flame temperature, heat release, etc. were discussed in this. Some aspects of chemical kinetics, the rate at which reaction occurs, that also was discussed. Then in the third module, we discussed about the characteristics of premixed and diffusion flames, differences between them, how the color of a premixed flame and is different from that of diffusion, what are the emissions, soot formation in diffusion flames, etc. were discussed. Then we saw the burning of liquid fuels, where first ignition, then flame spread, then mass burning rate was done. Some theoretical calculation for evaporation, steady evaporation and steady burning were also presented in this. Now we move on to the fifth module, which is the burning of solid fuels. So, if you see gaseous fuels, when they say premixed flame, when we are discussing, gaseous fuels are very simple to analyze because of the fact that a gaseous fuel mixes with gaseous oxidizer and gaseous reaction takes place. It is homogeneous in nature. When you go to liquid fuels, the liquid fuel has a rate limiting step. That means the liquid has to evaporate to produce vapors. In the gas phase, the vapor will mix with air and combustion in the gas phase will take place. So, predominantly the combustion takes place in the gas phase. So, there is a intermediate step other than the mixing, that is the production of vapor, that is evaporation of the liquid has to occur. Now, moving on to the solid fuels, the complexity increases. So, here gases have to be released from the solid fuel, for which it has to be heated, similar to the liquid fuel where heat is received from the ambient and vaporization occurs. Here also heat is received from the ambient, gases are released, but the solid fuels have more complexity because of the fact that they may produce carbonaceous residues, or they may directly sublimate from solid to vapor, or they may melt to liquid, then they vaporize. So, other aspects are involved in this. So, in this module we will see about the burning characteristics of solid fuels. So, with respect to this, we will see important points such as the solid phase thermal decomposition, or what we call as pyrolysis. This is actually in simple term called gasification. So, the solid fuel has to be gasified, the gases have to be released for sustaining gas phase combustion or ignition. So, that is first aspect we will see. So, as the term thermal decomposition specifies that there should be a heat interaction from the surrounding to the solid phase, and due to which the gases are released from the solid to the gas phase. So, this heat interaction and corresponding mass transfer have to be properly understood. So, the second point is basically the heat and mass transfer causing ignition or subsequent ignition of the unburned fuel, which will lead to a flame spread, that has to be understood. So, here the ambient conditions are going to dictate, such as the flame spreads in a concurrent flow or a opposed flow. Okay, so such aspects have to be considered here. Ignition, subsequent ignition causing flame spread is the second aspect. Then, when the particular solid burns, the amount of heat released, which is dependent on the burning rate, has to be quantified. So, based upon the rate at which the solid burns, we can also categorize the hazardness of the solid fuel. So, the heat release depends upon burning rate. Burning rate depends upon how fast the gaseous components come out of the solid phase. So, that is the third important thing. Then obviously, we will also look for suppression of the flame. So, in the cases where we consider flammable substances used in some domestic and industrial applications, if there is an accidental fire, how to avoid flame spread, that is, there should be no flame spread. Similarly, how to suppress the flame if there is an accidental ignition. So, these aspects are very important to study about the features of burning of solid fuels. Now, why we want to do this? Because first of all, we want to evaluate the fire risk. Then, when commodities are stored, what is the safe separation distance between this? See, even a building itself can burn, which predominantly is a solid thing. For example, wood is used as construction material in several buildings. So, when they burn, what is the separation distance required between the buildings to avoid fire from one building to go to another building? Even if you take, say, some warehouses where commodities are stored. So, between two columns, what is the difference distance required? Between two columns, what is the separation distance required in order to avoid fire spread? So, those aspects have to be considered. Similarly, when you use different types of solid fuels in your applications, the fire load estimate is important. So, the heat released from the particular commodity has to be properly assessed. So, finally, when the solid burns, what is the impact on structure and what is the quantity of water needed? See, especially we are saying water as the suppression or quenching agent, because for solid fuels, water based suppression systems can be used. We have already seen this. So, there are several characteristics for solids when they burn. The main thing to be understood is the steps involved when there is an ignition, fire spread and burning, and if there is an accidental fire, how to suppress it, how to avoid flame to spread from one commodity to another commodity and so on. So, these are the aspects which you will be able to see in this particular module. As I told you, ignition is even in the liquid fuels we talked about first evaporation and ignition. So, evaporation is the first step which will produce some vapors in the gas phase and which will mix with the air, and a premixed flame can occur upon ignition, which we call flash or an spontaneous or instantaneous flame, a flash or an instantaneous flame. So, now ignition of a solid fuel will occur depending upon how much volatile gases are formed over the solid surface. So, take a solid surface and there is a heat flux from the ambient. So, Q dot G gas phase to the interface, let us say this is interface. Now, based upon this, the surface temperature will change based upon the initial flux. There will be some heat loss also from the solid. So, I will say QL, heat loss. So, based upon the balance between the incident heat and the heat loss, surface temperature will increase. So, based upon the value of surface temperature, and also there will be some conduction here. So, I will say Q conduct. So, based upon the heat loss, the incident heat loss from the surface to the ambient, heat conducted within the solid, etc., the surface temperature will reach a value. Based upon the value of the surface temperature, volatile gases can be released from the solid surface. Now, this process is called pyrolysis, where the gaseous substances get released from the solid surface. Now, these gaseous substances will mix with the air, ambient air, and upon a pilot ignition, the ignition can occur based upon how much volume of this premixed reactants are available. Okay. So, ignition is defined as observing a sustained diffusion flame which can cause a sustained diffusion flame can cause further ignition without the need of external heat source. Okay, so that means that if you try to have a solid surface and try to heat it and ignite it so that a flame forms, this flame is the diffusion flame. Fuel vapors or fuel gases come from the solid surface to the flame, and the ambient air, oxygen from the ambient air comes to the flame surface. This flame itself can heat the solid and produce more vapors, and it can spread. So, the ignition is the formation of this diffusion flame over the solid surface, and it can spread over the solid surface basically. So, this needs an external heat source initially and pyrolytic ignition to cause this flame to be formed. Now, when the solid fuel is heated, see cone calorimeter or FPA apparatus, anything, it should be subjected to a heat flux or heat load. What happens is there is some structural changes within the solid, the molecular bonds break, etc. Then the volatile gases which are trapped inside, or basically gasification occurs, volatile gases are released. This is irreversible. Okay, now the word irreversible is important to understand. Okay, let us understand this. Let us take a beaker in which liquid fuel is there, liquid fuel. Upon heating it from the top, you get vapors produced. Now, this vapor can condense back to the liquid and liquid can evaporate to the vapor. There may be a phase equilibrium. Phase equilibrium between the vapor and the liquid at the interface. So, that means I can evaporate as well as condense. That is not irreversible. So, reversible process. When phase equilibrium occurs, the number of molecules leaving the liquid phase to the vapor phase will be same as the molecules entering the liquid phase from the vapor phase. But when you take pyrolysis of a solid, the volatile gases just go out, that is it. And these volatile gases are also called pyrolysate. And once the gas go out, they will not condense back to the solid surface, they cannot. So, it is an irreversible process as far as the solid fuel is concerned. That means pyrolysis is much different than the evaporation. In the evaporation, local phase equilibrium can exist where the vapor can condense back to the liquid and liquid can evaporate to the vapor and so on. But in this case, once the molecular decomposition occurs, molecular bonds break, etc., then what happens is the gases release out of the solid fuel to the gas phase, and then the condensation is not possible. It may come to the surface, but again it cannot go and rebond itself. So, pyrolysis is quite different than evaporation. That means it is complex. One more point is, we have seen about the liquid fuels are, the liquid fuel, the surface temperature of the liquid fuel becomes almost constant. When, see for example, for the given ambient temperature, the surface temperature becomes almost constant because of the fact that it reaches a thermal equilibrium, or we can say thermodynamic equilibrium with respect to the amount of heat coming in and amount of vapor leaving the surface. So, this equilibrium temperature we have seen procedure to calculate. On the other hand, if there is a solid fuel, the temperature need not be constant, it will increase. So, for the solid fuel basically, when heat flux come in, the mass flux go out, T surface can keep on increasing if there is a higher amount of heat which is coming in. and the mass which is going out will take its own enthalpy. So that if you compensate for these two, the surface temperature can keep on increasing. There is no definite temperature at which the surface will remain. Okay. So, that is another important difference between this. So, at evaporation stage, we can say, if we already seen that if the ambient temperature T infinity is lesser than the boiling point, then the Ts will go to a constant value just below the ambient temperature. If the ambient temperature is above the boiling point, then the Ts will approach the boiling point, will be some few Kelvin less than the boiling point. So, we have seen this, but in this case, if the ambient temperature is say 1000 degrees, the surface temperature can go as high as 900 degrees. For example, I am saying, so 800, 900 degrees it can go. So, that means there is no limitation. Now, the pyrolysis can occur at a given temperature called pyrolysis temperature. When the surface temperature reaches a temperature called pyrolysis temperature, then the gases will be released. So, at that stage the molecular bonds break and the volatile gases release. So, pyrolysis temperature is a characteristic, but after volatiles are released, pyrolysis temperature need not be a constant, like surface temperature need not be exactly at the pyrolysis temperature, it may increase also as the pyrolysis is happening. Okay. So, the minimum temperature at which the volatile gases will be released will be the pyrolysis temperature, but after that also the solid can be continuously heated up. So, these are very important points which should be noted and understood with respect to the pyrolysis versus evaporation. Now, in the case of heating of this solid, it may be due to convection. So, convective heating, so that means solid layer is there, solid surface, some hot gases can pass through the solid surface. So, it is called convective heating. When the hot gas passes through the solid surface, the convection heat transfer will be there. That will be a corresponding heat transfer coefficient H and delta T, which is nothing but T infinity minus Ts. So, that will be the convective heating. Similarly, there can be a cone calorimeter type of apparatus in which the high temperature surface will be there, that will radiatively heat the solid surface. So, thermal radiation from the surroundings. Even flame also, sooty flames also can heat the surface due to radiation. Similarly, conduction also can be one mode of heating the surface. Okay. So, some hot element can be used for heating surface and so on. So, typically all the three modes of heat transfer can be used as heat source to heat up a solid, causing its temperature to increase to the pyrolysis temperature that can cause the volatile gas or the pyrolysate to release. Now, ignition initiates the fire. After the fire is initiated, it will grow, that is the fire spreads over the material, the heat release rate which was initially small will increase and so on. So, this growth stage will occur. Now, as how fast the fire spreads on a particular object or between the objects or from one room to other room in a building and so on will determine the growth rate of the fire. If it is very fast, then we can say it is a fast growing fire. So, again some important properties of the solid have to be used. See here, basically how fast the pyrolysis can occur will determine the growth rate of the fire. So, the ambient conditions from which the solid surface is going to be heated, that is the important parameter here. If the rate of heating of the solid is higher, then from the initial temperature of the solid, which can be the ambient temperature itself, to the pyrolysis temperature, that heating rate will be very high. So, that is one of the points we should observe. Now, one more difference is there between evaporation and the pyrolysis process. So, we will see that little bit later when we talk about the charring fuels. So, here important points which are made are ignition depends upon the flammable mixture which is formed over the solid surface. The flammable mixture is formed when volatile gases which are released from the solid mixes with the ambient air, and ignition should lead to a sustained diffusion flame. First point. Second is, to cause volatile gases release, we need to subject the solid to a heat load where the molecular bonds will break and the volatile gas will release. And pyrolysis process is irreversible process because there is no thermodynamic equilibrium between the gases which are released and the solid itself, as opposed to a liquid in which the liquid and vapor will be in equilibrium, phase equilibrium which we can say. So, at a given temperature and pressure, the liquid surface can be at a given temperature, and now the vapor pressure corresponding will be such that the number of atoms or molecules which are going to escape from the liquid phase to the vapor phase will be same as that comes from the vapor to the liquid phase. That is called phase equilibrium. There is no such concept like that in the solid fuel. Next, all type of heating modes are possible in the solid. Basically, the thermal radiation part basically is not so high in the liquid fuels because of the radiation characteristics of the liquid fuel surface. But on the other hand, for solid fuel surface, radiation heat transfer can become very predominant mode. Okay, so pyrolysis, ignition, etc. will determine the growth rate of a fire because it controls the spread of fire between the objects or from one compartment to another compartment. Now, let us talk about time to ignition. Okay, so time to ignition for a solid fuel. See, in the liquid fuel case, time to ignition is determined as, or we have found that it is controlled by the evaporation rate. That's it. And basically the evaporation rate is dependent on not only the heat transfer but basically on the mass transfer also for liquid fuels. So that means the concentration gradient. So if I say liquid surface, so that is a YFS, the mass fraction of fuel at the liquid surface, and there is a YF infinity. This gradient of the mass fraction at the surface, what I say as dyf by dx. So this is x direction at surface, that determines the evaporation rate. So the evaporation of a liquid fuel is basically mass transfer controlled. So please understand that this YFS is dependent on the surface temperature Ts. The ambient temperature can be very high, T infinity, which can be a flame also can be over the sustained over the liquid surface. So this ambient temperature is high. So based upon this ambient temperature, Ts approaches the boiling point and YFS approaches a very high value, say 0.9, something like that. So now you can see that in this case the heat transfer becomes limited because after one particular value, say very near to the boiling point, the surface temperature cannot increase for the liquid fuel. So the heat transfer settles down, there is nothing much it can do. But if the vapors which are formed over the liquid surface, if they are removed at a faster rate, then the gradient of this dyf by dx will increase. Then the evaporation rate or the burning rate will increase. So for liquid fuel, the mass transfer can be a very important parameter which controls the evaporation rate. Now coming to the solid fuels, the time to ignition is controlled by several parameters. First of all, temperature, pressure, oxygen concentration and any convection, velocity of the gas surrounding the solid. Okay, so solid surface, the ambient temperature, ambient pressure, any velocity, then oxygen concentration. These are the factors which will primarily affect. So now obviously if temperature is higher, oxygen concentration is say higher, etc., or you have a convection, then what happens is a hot flow goes past the solid surface, convection heat transfer coefficient will be higher, then the heating rate will be higher, the Q which is coming to the solid will be higher. So, factors affecting are these. So, now when the heat transfer is higher, then the rate at which the solid is heated will be higher. That means from the initial temperature of the solid to the pyrolysis temperature, the time taken will be less. On the other hand, if temperature is low, oxygen concentration is less, velocity is less, etc., then you can see that the time taken for heating up the solid to the pyrolysis temperature where the volatiles will be released will be lower. Then radiation, as I told you, radiation is very important. So, incident radiation, what is the magnitude of that, whether it is uniformly distributed over the surface or spectral quality, etc., will also be important factors. Similarly, third one is the geometry of the solid, the thickness. When I say thickness, I mean physical thickness. So, if this is thickness, T P I will say physical thickness. This thickness, if it is high, what happens? Then the heat which is coming in is conducted inside, and you will have more heat loss because of the conduction inside the solid, and there will be some loss from the surface to the ambient also. So, if the thickness is less, then based upon the substrate boundary condition, the solid will be heated up faster. So, the time to ignition will be faster and so on. Similarly, surface area which is exposed to the incident heat flux. If it is larger, then obviously for any heat transfer problem, surface area is one of the factor which increases the heat transfer. See, for example, if you have heat exchangers, why we put fins and other things, try to increase the surface area because of the fact that the heat transfer will be faster. So, surface area is one of the important things which will contribute to both heat transfer as well as mass transfer. Surface area is important factor. Now, we already seen the location and the size of the pyrolytic ignition source. So, as a solid surface, it is heated up to some temperature, say Tp, pyrolysis temperature, so that the volatile gases come out. Now, if you keep the ignition source at a location which is very close to the surface, then it will be a fuel rich area, it will not cause the ignition and so on. So, that is a correct location where the ignition source will be kept in order to cause the ignition. So, you have already seen that if it is too far from the surface, again it will be very lean, fuel lean, it cannot ignite. So, the mixture should be within the lower flammability limit and higher flammability limit to cause the ignition to occur. So, pyrolytic ignition source, where to keep it, what will be the minimum ignition energy, etc., should be properly calculated. Now, as far as the solid is concerned, it can be horizontal like this, or it can be completely vertical like this. If it is vertical and gravity acts in this direction like this, if I try to ignite here, a flame forms and the flame moves from the bottom to the top, and the buoyancy induced flow also will be from the bottom to the top. So, this is the concurrent flame spread. If it is ignited at the top, it will be opposed flame spread. Okay, now, in the case of horizontal oriented, the other extreme, if I ignite somewhere here, a flame forms basically over the particular location. But if there is no velocity in this direction, the flame will spread only very gradually, because the gravity is in perpendicular direction to the surface. It cannot influence the entrainment rate also, but unless otherwise you have a force convection, you cannot determine the propagation cannot be accelerated. For example, if the flame spreads from left to right and the airflow also is from left to right, then you can see that it is a concurrent flame spread, or it will be opposed. If you ignite the other end, it will be opposed. but the gravity will not play much role in this particular phenomena. When the orientation is vertical, then the gravity will play a major role, because buoyancy induced thing will come. Okay. So, the aspects of ignition depends upon the orientation of the surface with respect to the gravity. So, this is very important. So, how strong the buoyancy is induced, the corresponding flow field etc. will trigger higher value for the heat transfer coefficient. So, more heat will be there imparted to the solid surface. So, in addition to these parameters, there are some internal factors also which will control the time to the ignition. So, time to ignition is very important. So, ignition delay, what we can say, that is very important. Several factors affect it.